So yeah, thanks for having me. I'm Chris Lynn. I'm a postdoc at the City University of New York and Princeton. I'm going to talk with you today briefly about some work that I've been doing with a talented grad student, Caroline Holmes, and my advisors, Bill Bialik at Princeton and David Schwab at CUNY. So in this project, what we've been trying to understand is how the arrow of time or the irreversibility in a collective system arises from the dynamics of the individual elements in that system. So just so we're all on the same page, I just wanted to quickly state for the record what I mean when I'm saying reversible and irreversible and broken detail balance and things like this. So suppose you have a simple system here with 4 states, so 2 of the states being x and x prime. What we're going to be talking about this whole time is these joint transition probabilities. So the probabilities of being at state x and then going to state x prime. So for a reversible system, what we have is that these transition probabilities are equal to their time reverse, and this is, as we know, just the detail balance condition. Now, by contrast, if a system is irreversible, that obviously means that the system simply breaks detail balance. There's some pair of states where the probability of going from x to x prime is different from the reverse. So for example, here you can clearly see that the probability of going from x to x prime is bigger than the reverse. And so you could be able, if you played the system backwards in time, you could tell the difference. And so we call the system irreversible. Now, across biology, irreversibility shows up nearly everywhere in every system and almost every function that you'd be interested in studying. So for example, at small scales, irreversibility is necessary for kinetic proofreading and things like computations. At the cellular level, you need irreversibility for adaptation and sensing, and even at high levels. So for example, in whole brain imaging, it appears that irreversibility is important for things like higher level cognition. Now, in basically all of these systems, in almost every system where we're interested in thinking about irreversibility in the arrow of time in biology, the systems themselves are composed of subunits. So they're almost all collective systems that have these individual elements that are either behaving independently or interacting with one another that then produce this macroscopic arrow of time. And this raises a very clear question, which is, how does this collective irreversibility that we see arise from the dynamics of the individual elements in the system? So just a quick outline, what we're going to do is we're going to try to quickly build a framework for answering this question. And then we're going to, at the very end, try to apply this framework to actual data of collective neuronal spiking in the retina. Okay, so just to begin, it's going to be helpful for me to state exactly what I mean when I say irreversibility. So what we're going to be talking about specifically is what we're calling local irreversibility, which is the irreversibility contained in individual transitions. So you could also think of this as sort of the Markovian irreversibility in the system. And the way we're going to quantify this is using information theory. So information theoretically, in a very precise sense, the Kale divergence between the forward and backwards transition probabilities is precisely the evidence that you gain by observing the dynamics about the arrow of time in the system. And this is also just a quantity that we've all become very familiar with, obviously. So just to set our intuitions again, if we look at this reversible system, the forward and backward transition probabilities are equivalent. And so this Kale divergence is 0 and we have reversible dynamics. And then any difference between the forward and backward transition probabilities will give rise to non-zero Kale divergence. It will give rise to irreversibility. And then also, as was being discussed this morning, under some conditions that Jordan Horowitz could clarify, if in some systems, what we're calling the local irreversibility is actually the entry production in the system. And if this is the case for whatever system you're interested in studying, you can just tune out when I say irreversibility, just think entry production. You can use this whole framework to decompose the entry production in your system. Okay, so really what we're interested in understanding is where irreversibility comes from in these collective systems. So does it come from the individual dynamics of individual elements? Does it come from pairwise dynamics, triplet dynamics, or some complicated higher order dynamics in the system? Now, to answer this question, what we can do is we can imagine observing just k elements at a time So imagine we have n elements in our system, and then we observe all the groups of size k in the system. Now, what we could ask is can we come up with a hypothetical system that is consistent with the kth order dynamics in the system that we observe in the data, but otherwise has minimum entry production or minimum irreversibility? So this would give you this quantity I superscript k is the minimum irreversibility consistent with the kth order dynamics that we observe in the data. And I just as another quick aside, the notion of minimizing irreversibility or entry production with respect to some constraints dates in some sense back to all the way back to Prigozhin and Schnackenberg, but also more recently, there's been some cool work by Skinner and Dunkel looking at similar questions of minimizing irreversibility with constraints. Okay, so if we're able to compute these sort of kth order minimum irreversibilities, what we end up with is a hierarchy of lower bounds, because the information contained in the kth order dynamics contains all of the information about lower order dynamics. So you can only get a higher upper bound as you include more and more information about the dynamics in the system. So for example, if you tell me absolutely nothing about the system, I can still say that the irreversibility is greater than or equal to 0 because it's a KL divergence. And this is obviously also just a restatement of the second law. Now, let's assume that we include some very simple information about the system, the information about individual elements. Then we get a slightly higher lower bound. You could include information about pairs of elements, you get an even higher lower bound, so on and so forth. Until if you include information about the entire system, so you have a full description of the system, then you obviously just recover the full irreversibility of the system. Now, at the end of the day, really what we want is the irreversibility due to kth order dynamics alone. And so we're gonna define what we call an interaction irreversibility of order k, which is just the minimum irreversibility consistent with kth order dynamics minus the minimum irreversibility consistent with the lower order dynamics, the k-1th order dynamics. So intuitively, this is just the extra irreversibility you get by including kth order dynamics in your description of the system. And now once we've defined this, and I should say that this interaction irreversibility by definition is greater than or equal to 0 due to this hierarchy of lower bounds. So what we get is what we set out to get at the very outset is a decomposition of the full collective irreversibility of the system into these n non-negative components corresponding to first order irreversibility, second order irreversibility, and so on and so forth. Cool. So this is the framework that we set out to build at the beginning. So let's try to apply it to an actual biological system. So the first system we thought to apply it to was collective spiking in the retina, and the reasons are twofold. So first of all, the retina is an inherently collective system. The neurons don't encode information about the visual world individually; they do so as a collective unit. And secondly, basically all of the information that the brain has about the arrow of time in the visual world passes through the retina. So for those two reasons, cool, thank you. So for those two reasons, we thought the retina would be an interesting sort of system to begin studying. So what we have here is a salamander retina, and we start off by showing it a naturalistic movie. So for example, a fish swimming in a tank, as you can see here. And I should mention that this movie is inherently irreversible, because if I played it backwards, you could see the fish swimming backwards, and you could tell the difference. Now, when you're estimating these irreversibilities, these KL divergences, it's important to make sure that you're sort of accurately accounting for the finite data effects. It's sort of a tricky business to estimate KL divergences from data. And what we find is that we can accurately estimate the KL divergence or the irreversibility in groups of up to 5 neurons, but not bigger. So what we're going to study is groups of 5 neurons. So in random groups of 5 neurons, what we find is that when they're looking at this naturalistic movie, roughly 2/3 of the groups break detailed balance statistically. So they have a significant irreversibility with values shown in this histogram. Now, what we can do is we can show the retina, the same groups of neurons. We can show them a different stimulus that is inherently reversible by definition. So this stimulus is just a horizontal bar that's moving up and down on the screen. with motion defined. It's just Brownian motion attached to a spring that's attached to the center of the screen. It's an inherently reversible dynamics. Now, when we show the same neurons this stimulus, what we find is that the irreversibility of the neurons actually increases. So somehow there's this interesting non-trivial relationship between the irreversibility of the visual world and the irreversibility of the retina, which we don't fully understand. But at the end of the day, really what we want is to apply our framework to understand where this collective irreversibility in these groups of neurons is coming from. And what I'm plotting here on the x-axis is the order of the dynamics, so from 1 to 5. And on the y-axis, what we're plotting is the fraction of the irreversibility that arises due to those kth order dynamics. Now, I should mention here that for binary steady state variables, the independent irreversibility, so the irreversibility of just one binary steady state variable has to be 0. At least the local irreversibility, the Markov irreversibility has to be 0. And we do find that our neurons appear to be behaving in steady state. So by definition, this sort of first order irreversibility has to be 0, which means that all of the irreversibility in the groups has to arise from sort of collective dynamics. And in fact, we find that across both of the different stimuli, roughly 70% of the irreversibility comes from the simplest possible dynamics it could, which is these pairwise dynamics. So just to conclude, we built this framework for decomposing the irreversibility in interacting systems. And we applied it to these sort of groups of neurons firing and found that the irreversibility depends highly non-trivially on the irreversibility of the stimulus, but across both stimuli seems to arise from the simplest dynamics, these pairwise dynamics. So we have a couple papers on the archive about this, if you'd like to check them out. And I'd just like to thank my sort of collaborators and funding. And thank you all for listening.